Okay, welcome back to EE210B. So today we are going to continue our studies on the stability of distributed networks, right? Of distributed algorithms over networks. So I started this discussion last time and we are going to continue it today, and I already warned you, right, last time that this is a little bit demanding. It's not difficult, but it requires some effort for you to follow the arguments. Okay, so it will continue today, and these happen to be technically the two most demanding lectures in the course. Okay, not that they are difficult, but it's where you see many of the results from earlier lectures applied together and used together here to answer important questions about the stability of networks, right? And these arguments also tell you that this is not a trivial topic. It requires some effort because of the coupling that you have between the agents. But fortunately, we are able to do it, and you are going to see how we do it. Okay, so I'm going to continue the material from chapter 9, and I indicate the pages over there. So this lecture also is based on material from chapter 9, and the text is the one that you have listed over there. If you remember, last time I proved the last two statements on this slide, right? I proved that if you run a distributed algorithm to solve an optimization problem or an adaptation problem or a learning problem over a network, a strongly connected network of agents, and if you define the error vectors, so this is the error vector at agent k at time I, right? This is the difference between what you have and where you are going to, and that's the Pareto solution, right? The W star. We showed that the mean square error and the fourth order error, right, in the limit, they enter regions whose sizes are of the order of the step size or the step size is squared, right? This is the maximum step size across the network, okay? So it's of that order. And since the step size is usually very small, so this tells you that for all practical purposes, these algorithms are stable, right? Whether you look at it from the perspective of the second order moment of the error or the fourth order moment of the error. This is what we proved last time, right? Today, I'm going to complete this theorem and prove the first statement, plus a few other results that we are going to use next time, okay? So today, the emphasis is on proving that the limiting value of the norm of the mean error vector, that also is of the order of the step size, okay? And this will require some effort. When all is said and done, right, when you come back and you look at this statement, what this statement is telling you is that these algorithms, even in the presence of gradient noise, they operate in a stable manner over networks, right? What we are going to do in future lectures, and especially in the next lecture, is the following, like we did for single agents and for the centralized solution. So this is entering an area of this size. Tell me exactly what that size is, or give me a reasonable approximation for that size, because this essentially means it's a multiple of that. Tell me what that constant is. That's essentially what we will be doing, right? Deriving the MST expression, mean squared deviation expression, in the future lecture. Okay, so let's continue. Okay, so let's focus on that first statement. Okay, now remember, for any random variable A, let's say A is a real random variable, right? This inequality always holds. Why? Remember that, what is the variance of a random variable x? It is the expected value of x squared minus the mean of x, right? All squared, and by definition the variance is always non-negative, right? So for any random variable x, it holds that this quantity is smaller than or equal to that quantity, right? Which is what I have written here, correct? So if I apply this inequality to this particular random variable, which is the Euclidean norm of the error vector at agent k, right? Then you will get that the expected value, right? So the expected value of this norm, right, squared, right, in the limit, so I'm talking about it in the limit, okay? So in the limit, it will be upper bounded by the expected value of the norm squared, which we already know is of the order of mu max, right? And then if you take the square root of both sides, that's where you get this expression here. So in principle, I can conclude from the result that I showed last time that the mean square error enters a region of size mu max, that the expected value of the first order moment, right, the norm only, not the norm squared, will enter a region whose size is also of this, is the square root of mu max. Now, the square root of mu max, when mu is very small, is larger than mu, right? For example, if mu is 10 to the minus 6, square root of mu will be 10 to the minus 3, right? 1,000 times larger, okay? So even though you can get a bound like this, we are interested in a tighter bound, okay? So what I'm going to do, I'm going to derive a bound for this norm instead, the norm of the mean, rather than the mean of the norm, okay? So I'm going to show that the norm of the mean, we can bound it by O mu, right? That's the first statement of the theorem, okay? That's why this requires a little bit more effort, because this result, we can get it already from what we know. But what I want to show is a tighter bound on the norm of the mean. Okay? Very good. So this is the motivation. So let me remind you what we did last time. Of course, I'm not going to derive this again, but if you remember last time, and perhaps the lecture before that, I derived the error vector, the error recursion that tells me how the error evolves over the network, right? So just to remind you of the notation, W tilde I is the vector that contains all the individual error vectors across all n agents, right? W tilde 1, W tilde 2, W tilde n, right? The E is because each one of these is actually extended. So W tilde 1 contains W tilde 1, and then you star it and you transpose it, right? So each one of them becomes 2m by 1. That's because you are dealing with the general complex case. Otherwise, you don't need to do that. You can just remove the E if you are dealing with real data, right? Very good. So this is the error vector, the network error at time I. This is at time I minus 1. This is the gradient noise, again, right? At every agent, you are using the approximate gradient vector. So the difference between the approximate gradient vector and the true gradient vector is the gradient noise at that agent. You put them together into a big vector, it becomes the network gradient vector, right? Okay, and then this is the bias vector. If you remember, the gradient vector, the true gradient vector evaluated at W star is not necessarily 0, right? Because the W star is not a minimizer for the local costs, right? So we collected all these gradients, which are constants, right, into a bias vector. Again, they are extended. Fine? And these quantities, this M here is a block diagonal matrix containing the step sizes, right? A2, A0, A1 are the combination matrices, right? Kronecker identity of size 2M, right? You extend them. And the only thing left is that matrix B, and this is the matrix B here. It has a constant term, right, and a random term, okay? And the random term was defined in terms of a block diagonal Hessian matrix, right? So this H is block diagonal. Each one of these H's, so I'm using this symbol H because they are related to the Hessian of the costs. So here it is. Each one of them is an integral of the Hessian of the cost at the corresponding agent, evaluated at some location, right? We don't really care much about the exact expression for these H's because when we did the analysis, we called upon the fact that your costs are strongly convex, therefore uniformly bounded from below, and we also assume that they are uniformly bounded from above, because we assume, okay, we assume that the global cost was uniformly bounded from below and from above, right? And at least one of them was strongly convex, and that led us to say that we can bound these quantities, right? Okay? So the exact expression is not as important as the bounds, because from the bounds we can, okay, we can deal with this expression. So you remember this? Okay, so what I'm going to do now, I'm going to work from here. Last time I used this recursion to show the last two properties in the theorem I showed you before, that the second order moment and the fourth order moment are bounded in the limit in the manner I showed you. Okay, very good. Okay? So now let's look at the mean. So if I take the expectation of both sides here, right, the expectation of both sides, gradient noise, if you remember, this is one of the assumptions we had, gradient noise is zero mean, right? So this term here is going to disappear. This term is not random, so there is no need for expectation here. You are only left with that, right? So when you take expectation of both sides, this is what you get. This tells you, okay, how that mean is evolving. But remember, B is random because it has this H, so I still have a problem here, evaluating this expectation, because this has the H's which depend on the W tilde, so here you have some coupling, okay? So the way I'm going to go around this, I'm going to take this B which is random, and express it as a constant B plus a B tilde, okay? So the constant B, then I can take it out, and that B tilde will contribute a term here, and that term I'm going to show you that for all practical purposes it is a small, of the order of mu squared, okay? And that constant B that I'm going to get here, I'm going to show you that it is a stable matrix. Okay? So I will end up with a stable recursion driven by something that's small, and I will be exploiting these two properties to conclude that first statement of the theorem. So this is the plan, you understand? Of course, I need to show the details, but this is the plan. I'm going to split this into a constant B plus a B tilde that will drive here, show that this is a small, show that that B is stable, and then come back here and conclude what I want to conclude, okay? So it will take us some effort to show these things, but that's what I'm doing, okay? So let's do it. So here it is. Now remember, this is my B here, right? This is my B. So what I'm going to do, I'm going to take this H, write it as a constant H plus an H tilde. You see, so this H here, I'm going to define an H tilde. Let me write it here, and then I'll go to this slide, which is some constant H minus that H. What is the constant H? This constant H, I'm going to define it like this, but it will contain, so it's a block diagonal matrix, it will contain the Hessian matrices of the individual costs at W star. You understand what I'm saying? So this is a constant matrix, right? This contains the Hessian quantities at the W star. So a block diagonal matrix, which is a constant. The difference from this, I call it H tilde. So now by doing this, I can replace this H by what? By this H minus that. So I can replace this by a constant H, and then I'll have another term with an H tilde in it, right? The constant factor with P, I group them together. That becomes my constant B. So this Bi minus 1, I'm writing it now as some constant B, which I'm constructing from here, essentially replacing this by a constant H plus the rest. That term will contribute the additional third term in the recursion that I referred to, right? That's where the analysis, okay? So this is what I'm doing here, you see? So I define the difference. Here it is. This H is block diagonal, where each one of the H's is the Hessian matrices, right? This is what I define. So now if you go there, I replace that H by the constant H and the H tilde, correct? Okay, so these two, I group them into a constant matrix B. Okay, so it has exactly the same form as the random B. The only difference is that its random H was replaced by a constant H. Correct? This B will play a major role in our analysis, okay? And the rest, this is the rest, right? So I'm introducing a particular symbol for that B here, because for this combination here, I'm calling it B because it's an important matrix, yes.
Professor, how did we know that we can write H as a constant term plus a random?
That's a definition, right? It's just definition here, right? I'm just saying, let H tilde be this difference, right? Introduce this H, call this difference H tilde, and therefore now you can write this as H plus H tilde, right? Okay, so this is just definition. Okay, fine so far? So then, now if I go back to that recursion I had before, which had the random B here, I replace this random B by the constant B plus the rest. So the constant B now goes outside here, and the rest comes here. So what was the rest? You see, the rest was A2 transpose M H tilde A, right? You can think of it as a delta B, right? So that rest was multiplying W tilde, and it had an expectation also, right? So that rest would be this multiplied by W tilde times an expectation, right? Okay? So what I'm doing here, A2M, I'm keeping it out because it's a constant, right? And the expectation, put it here. So this C is simply a shorthand notation for the expected value of H tilde A1 transpose W tilde I minus 1E, right? Because I cannot take any further out. Because this is a constant, this is a random, not a random, this is an expectation. Fine? Okay? So you see, if I compute the norm of C squared, you can see already, if I compute the norm of C squared, it will be related to the norm of this squared, which I already know is bounded in steady state. So that's where I will be able to bound this. Okay? So you understood what I did so far? Okay, very good. So I'm going to come back to this recursion later to conclude what I want to conclude. But now there are two things I need to study first before I can come back to this recursion. First, I want to show you that this B is always stable for small step sizes, always stable. And second, I want to show you what's the bound on this. And then these two facts, I'll use them together to conclude that first statement of the theorem. Fine? This is the strategy. Okay? So this is C here, okay? This is C. So let me start with B, and this will take some time, okay? Let's start with B. So I want to show that, and then I'll come back to C, right? And then I'll group them together, okay? By the time I'm done with this, you would have forgotten what I'm talking about. That's why I'm repeating it, okay? Fine, okay. So B is a stable matrix. I'm going to show it for small step sizes. And moreover, the spectral radius of B is of this form. It is 1 minus the minimum eigenvalue of this combination of the constant H's. Remember those Q's, they are defined in terms of the Perron entries of the matrix P, right? So, okay, we defined them last time. You remember that, right? Those entries Q here, okay, they were defined. So you take the step sizes multiplied by A2 by P, right? Those are the entries, and they are positive, okay? So what this is saying is the following. This sum here is a positive definite matrix. So the minimum eigenvalue of that will be positive. And these Q's, they are of the order of the step size. So this is like 1 minus a positive number of the order of mu, okay? And this is a higher power of mu. You see, m plus 1 over n is larger than 1. That's all you really need to know from this. Because this is a higher power of mu, when mu is very small, this order, right, is smaller compared to O mu. So this is the dominant factor, okay? And this will be of the form 1 minus something of the order of mu, which will make it stable if the spectral radius, right, is less than 1. Okay? And this quantity is important because it will determine the speed of convergence of your algorithms. It will be this quantity here. I'll come back to this later. But this is where it comes from, that the spectral radius of B is given by this. Let's prove this. Okay? Now, remember that, okay, what was the B? Let's go back to the expression for B. This is the B. Okay? This is the B. I want to show that it is stable. You know, it's very easy to show that it is stable for diffusion, very easy. More challenging for consensus and more challenging in general, okay? For example, remember for diffusion, 2 A's will be identity, 1 A will be left, right? Remember the general form that I wrote the algorithm, okay? So one of these A's will be identity, the other A will be some A in diffusion. And this P will be that A because it is the product of the 3 A's. Okay, so let's assume, where did I write P? Just so that you see here. Okay, so P, here it is, A2 transpose A0, A1. Okay, so this P is A2 transpose A0 A1. Let's take the case when these two are identity. So this is ATC, adapt and combine. So this B will become what? Will become A transpose times I minus MH, correct? That's the ATC diffusion case. For CTA, these two will be identity and A1 will be A. So in that case, you will get I minus MH A transpose, correct? Okay, fine. For consensus, this and that will be identity, this one will be A. So for consensus, you're going to get A transpose minus MH. Okay, so here it is. So for diffusion, the form of B collapses to this. So now it's very easy to see here that B is indeed stable. How? Well, that there is a small step size that makes it stable. How? I can use a result from an earlier lecture, which says the following, right? This matrix here is block diagonal, right? M is block diagonal, H is block diagonal, I minus that is block diagonal. Number one, it's Hermitian. And if you remember, we had to resolve that. If I have a block diagonal Hermitian matrix and I multiply it by a left stochastic matrix from left or right, the spectral radius of the product is upper bounded by the original spectral radius, right? Multiplying by left stochastic matrices does not increase the spectral radius, correct? Now, I can choose the step size to make I minus MH stable, right? Because this is simply block diagonal matrix, right? It will have I minus mu1 H1 and then repeated on the diagonal, I minus mu2 H2, right? Each one of them can be made stable. If you choose mu k to be less than 2 over the spectral radius of HK, correct? Right? So here it is. If you choose your step size to be less than that, the I minus MH will be stable, and therefore the B corresponding to diffusion, whether it is ATC or CTA, is stable, right? So there is a sufficiently small enough mu that makes diffusion stable. So it's very easy to prove it in the diffusion case, correct? Okay? You just get it from this. And this also confirms what I said before. If the non-cooperative system is stable, because this is the dynamics for the non-cooperative system, when all A's are identity, diffusion will be stable. Okay. What about consensus? Okay, so let me remind you first of this theorem that I stated before when I reviewed matrix results with you. Wiles theorem. Let's first review it. Assume I have a combination of three matrices, okay, where A prime is A plus delta A. Okay, they are Hermitian matrices, and I'm ordering the eigenvalues. I use lambda 1 for the largest. Since they are Hermitian, they have real eigenvalues, so I can compare them, right? So lambda 1 is the largest, lambda n is the smallest. This is my notation. So now, if I change A by a little bit, add a delta A to it, or a lot, it doesn't matter. If I change A by some delta A, how do the eigenvalues of A and A prime relate to each other? This is what this theorem says, you see. If you change A by delta A, then how do the new eigenvalues of A prime relate to the eigenvalues of A? Okay, so you take the nth eigenvalue of A prime, you take the nth eigenvalues of A, right, here it is. Add the largest, add the smallest, right? So you get an interval. The new eigenvalue will lie within that interval. This is what the theorem says. I'm not proving it, I'm just stating it, okay? Fine? Okay? So the nth eigenvalue will lie within an interval, which you define from the corresponding nth eigenvalue of A in this manner, okay? You add the smallest value here, the largest value here, so you get an interval. This eigenvalue will lie within that interval, okay? This is what this theorem says. Now, let's see how is this useful to show that the result of the theorem for consensus. I will be able to use this theorem when A is symmetric. Okay, what if A is not symmetric? Because very often A is not symmetric. Then the step C in this proof, which is in general, okay, will cover that case, okay? So let's assume for now just that A is symmetric, okay? A is left stochastic and symmetric, it becomes doubly stochastic, right? Becomes doubly stochastic. Now, if A is symmetric and if A is left stochastic, we already know that the spectral radius is 1, correct? Left stochastic matrices, the spectral radius is 1. The eigenvalues are all inside the unit circle, magnitude less than 1. If it is symmetric, then the eigenvalues have to be real, right? Then they have to lie actually in this interval between -1 and 1, right? They will have to be here. It will have an eigenvalue at 1. We know that for a fact, right? Okay. If that's the case, if all the eigenvalues of A are between -1 and 1, then the smallest eigenvalue of this, and remember, this has an eigenvalue at 1, the smallest eigenvalue of this difference is 0, right? Because it is 1 minus the eigenvalues of that. This has an eigenvalue at 1, right? Fine. The smallest eigenvalue of that is 0. And not only that, all other eigenvalues will be larger than or equal to 0, right? Because the eigenvalues of this are between -1 and 1. Okay. Okay. Now, let's introduce the B for the non-cooperative case, okay? The argument is simple, okay? Don't be alarmed by the algebra. The argument is simple. Just follow it, okay? This is B for the non-cooperative case, right? I minus MH. And what is the B for consensus? The B for consensus is A transpose minus MH, right? So you see, I can relate them like this. This is A transpose minus MH. A transpose cancels that, you end up with I minus MH, right? The second relation, lambda min I cancel each other. You have A transpose minus MH, right? Nothing changed. So why did I write these relations like this? Because I'm writing them in the form A prime equals A plus delta A. A prime equals sum A plus delta A, and then I'm going to apply Weyer's theorem to it. Fine? You understand? Okay, so for example here, this is telling you that if I take, okay, so let's remove this. If I take, let's say, the nth eigenvalue of the non-cooperative B, right, this one, it lies between two bounds, correct? The nth eigenvalue of the consensus B plus something, and the nth eigenvalue of the consensus B plus something, right? What was this something here? The smallest eigenvalue of the delta A, right? The delta A, its smallest eigenvalue is 0. So I get what I wanted. I only want one part of this relation, that the nth eigenvalue of the consensus B is always upper bounded by the nth eigenvalue of the non-cooperative B, right? This is exactly what I wrote here. And the same argument for the second relation, you can just do it. Same argument for the second relation gives you use the other side now, the upper bound, that the nth eigenvalue of B consensus is upper bounded by the nth eigenvalue of this difference. Fine? Okay. Now, why is this useful? Because remember, if I want consensus to be stable, right, I need its eigenvalues to lie between -1 and 1, because B consensus, under the assumption that A is symmetric, it is a symmetric matrix, so the eigenvalues will be real. So for it to be stable, I want its eigenvalues to be between -1 and 1, right? But these relations here, up here, I showed that any eigenvalue of B consensus lies between two bounds, right? This bound is here, correct? And this is the lower bound, is there, correct? So one way to ensure that this is between -1 and 1 is to make sure that this upper bound is less than 1, and this lower bound is larger than -1. Right? That's a sufficient condition. All I'm trying to show is that there is a small mu that makes that possible. Here it is. So I want the upper bound to be less than 1, the lower bound to be larger than -1, correct? Now, remember that the non-cooperative B is I minus MH, right? What are the eigenvalues of this? Okay, there will be 1 minus mu times the corresponding eigenvalues of H, correct? For very small mu, all these eigenvalues are slightly less than 1, right? So this first condition here, because of the structure of I minus MH, is automatically satisfied. This first condition is automatically satisfied, okay? What about the second condition? What are the eigenvalues of this? Well, lambda min of A, correct? Lambda min of A minus mu times some eigenvalue of H, correct? Okay, you want that eigenvalue. So this is just some simple algebra here. Let's say lambda min of A minus some mu, right? Times some lambda of H, some of the lambdas of H, right? You have many of these H's, okay? You want this to be larger than -1, correct? You can solve for mu. Okay, so if you do that, here it is. You can solve for mu. Okay. Here, you remember that these H's are Hessian matrices. Their eigenvalues, right, are positive, right? Their eigenvalues. So what you have here, if you have an eigenvalue and you replace it by the spectral radius, this becomes, right, a smaller number. So if mu is smaller than that, it will be smaller than what you need it to be, okay? But the important thing is that if mu satisfies a bound like this, then I will conclude again that the consensus B is stable. Fine so far? Okay. But does this bound make sense? What is the spectral radius of A? 1, right? The spectral radius of A is 1. And, and its eigenvalues are between -1 and 1. Right? So it has an eigenvalue at +1 and, okay, and the spectral radius and the lambda min, okay, remember, my network is strongly connected, right? So there is a single eigenvalue that meets the spectral radius, right? We already know that it has 1 at +1, so it cannot have an eigenvalue at -1. So that's why this lambda min has to be larger than -1. So the numerator has to be positive. So then this is a valid bound, okay? Right? So again, a small enough mu exists that makes the consensus B stable. But this argument required us to assume that A is symmetric. So we only proved it for a smaller set of A's, right? But I just want to, but for diffusion, we were able to show it for any A. Now, the next argument that I'm going to show you applies to diffusion, applies to consensus with symmetric A or non-symmetric A, and applies to general A's. You don't need to make two of them identity and the third A. Applies to a general product of A's. Okay, so this is the more general argument, okay? But I just wanted to show you the special arguments so that you get convinced that indeed that's the case. Okay, so this more general argument, I'm going to use eigenvalue perturbation analysis to prove it. Okay, I'm going to apply the Gershgorin theorem, which I'm going to review, and we saw it before, and we're going to see an application of it here. Okay, so what is this result? Okay, so let me remind you of some notation we introduced last time again. Okay, last time I started with the matrix P, remember, it was A2 transpose, A0 transpose, A1 transpose. It's the matrix that includes, sorry, it was A1, A0, A2, something like the product of the A's, okay? I don't remember the order now, but it's the product of the A's. We introduced its Jordan decomposition, but this was a special Jordan decomposition. First of all, because P is strongly connected, it has a single eigenvalue at 1. All other eigenvalues are strictly inside the unit circle. We collect them in J epsilon. So this has a Jordan structure, except that the ones on the first subdiagonal are replaced by epsilons, remember? Okay, and this is V epsilon here, V epsilon M. I call the matrix on the left V. The other one will be the inverse of it. Okay. Now the calligraphic P, because in all our expressions, calligraphic quantities appear, right? It's just a Kronecker product. So from this decomposition, I can get the corresponding decomposition of P, which I did last time. Okay, here it is. You just extend them. Again, calligraphic products. This is the Jordan decomposition for P, right? I did all of this last time. I'm just reminding you, okay? And then if you go to B, okay, if you go to B, what was B? B was, right? B was something like this. P transpose minus, okay, A2 transpose M H A1 transpose, right? This was B, okay? So if this is P, P transpose, you would just reverse the order here, right? P transpose, okay? So here it is. I have this times that is P transpose, correct? Minus this times D times that should be this quantity. And you see here that the way I define D, I include the inverses here so that they cancel each other, right? And you recover that quantity, right? This is what we did last time. Did you follow so far? So this D is defined like this, and last time I said let's partition this D into a 2 by 2 block matrix where D11 was 2m by 2m and the rest is there. And then last time I gave you the expressions for these quantities. We don't need them, but I'm just reminding you, I gave you the expressions for these quantities. The important thing was I showed that all these quantities were of the order of mu max, right? Okay, we don't really need the expressions except that to remember that these were all, the entries of these matrices were of this order. They are small, right? Okay, very good. Here it is. And that the spectral radius of I minus D11, because this is of the order of mu, was also of that form, right? We showed this last time. This is all reviewed. Okay, very good. So now, so here it is. So this is the matrix B that I wrote before, right? I wrote before the matrix B. Here it is, right? So rather than write this quantity like this, I'm going to call this calligraphic V, right? Here, calligraphic V, something like that, right? Rather than, and then I'm going to group these two terms together, okay? We also did this last time. This is B, right? I'm just writing B in terms of the D's, in terms of the J and I, okay? And if you take these eigenvector matrices to the left, what do you get here? You find that the matrix B, which we want to show that is stable, is similar to this. That's what this relation 206 is showing, right? Okay? So remember, I explained this to you last time, that this eigen decomposition, we introduce it. Why? We introduce it in order to partition the dynamics of B into this block structure, because the 1-1 block here, we are going to be able to show that it is stable, and the rest will be quantities that we can almost ignore, right? That's always the idea, okay, that this partitioning is important because of that, okay? So we did all of this last time, so I arrived at 206, okay? So to me, what 206 is saying is that B is similar to this. And I want to show two things. I want to show that B is stable, so I need to show that this is stable, that all the eigenvalues of this are inside the unit circle. And second, I want to find an expression for the spectral radius of this, because the theorem also gave that expression, right? Very good. Okay. So let's see how do we do that. All I know so far are that the eigenvalues of this are of the form 1 minus of the order of mu, right? And this D is positive definite because it's the sum of Q times H's. So I know that this is stable. The 1-1 block is stable. But what about the eigenvalues of the entire thing? I know that these are of the order of mu. This is of the order of 1 because this J here, right, has eigenvalues. Okay? Fine. So what about the eigenvalues of the big thing? So this is the eigenvalue perturbation argument that I'm going to use to show that, okay? And it's an interesting argument. You will see it. You may have heard of it before. You heard about it in this class. And this particular problem gives you a chance to see it applied to a useful problem, okay? In an interesting way. So this is what I know so far, that B is similar to this. But I want to get more. I want to show that B is actually stable. If you compute the eigenvalues of a matrix like that, all of them will be inside the unit circle. This is what we want to show. Very good. So to do that, let's look more closely at the structure of J. Remember that this J is an extended Kronecker product version of a J like this. Has Jordan blocks, right? When you take Kronecker product, what will happen? You will put I's here, right? That's all. You will put, these become, right, matrices, submatrices, fine, okay? There it is, okay? Now, so you have epsilons, right? So you have zeros, most of the entries are zeros and some entries are epsilon. And on the diagonal you have lambdas, okay? But here it is the transpose that appears, okay? So if you take the transpose of this, you just flip it, right? Okay? So this is the J. So I can write this J here as these diagonals plus something down here plus something down there whose entries are either 0 or epsilon. Fine? I don't need to be specific about the structure of K. Whatever is appearing here, I have either zeros or epsilon. Okay? But it is the transpose of that that appears, right? It is the transpose of that plus O mu. So let's go back. It is the transpose of that plus O mu that appears in B. Okay? So if I write the transpose of that, K becomes here, and then I add O mu to all of these entries, right? So all I'm saying is what is the order of the entries of that quantity that appears in B, okay? Very good. Okay, so now comes the argument, okay? I'm going to introduce, remember, D11 is Hermitian, right? And positive definite. So it has an eigendecomposition, right? Lambda will be diagonal with positive entries. I just want to make it simple. So let's introduce this transformation to diagonalize D. Fine? So introduce this matrix U. Okay, so let me define now a transformation, and you are going to understand why it's useful when I show it in use, okay? Let me take this U and define this transformation. What is this transformation? Let's look at it. It's a block diagonal matrix, okay? Block diagonal matrix. So you will have mu to the 1/2. I'm not going to write mu max each time. Mu to the 1/2, sorry, mu to the 1 over n, U, right? Mu to the 2 over n, U. Sorry. Okay. N here, U, and then I, mu to the 3 over n, I, and it keeps going like that until you get mu to the n over n, which is, right? It's a block diagonal matrix, fine? Okay, block diagonal matrix. So all of them are simply mu I, right? The multiples of the identity. So this is a block diagonal matrix. So I'm going to apply it again to this matrix, which is already similar to B. I still get something similar to B, right? But it will look a little bit nicer. If you do this, because I put the U here, remember that the leading block here was I minus D11. Because of this, then this will be diagonalized and replaced by lambda. Because when you multiply by T from one side, T inverse from the other, this 1 block will be multiplied by U star from left and right, right? U star times I keeps the I, but U star times D makes it lambda. You understand? That's why we put U there, okay? And then you are going to have mu, and then the inverse of that mu, then no mu appears here, right? So, when you apply this transformation to B, this is what you get, okay? This is what you get. Here, I'm calling it B. You get I minus lambda. I explained to you where it came from, right? What about the rest? The rest, I don't really need to know exactly what it is, except what their orders are, okay? So when you do the calculations, okay, this is what you are going to find. That all the entries that appear here are of this order. Okay? You see, remember, if you go back here, the entries in that column of B were what? Of the order of mu, correct? Of the order of mu. Now, you are going to come and multiply them from the right, so that this, so here, okay, here, this part of B is of the order of mu, correct? I'm going to come and multiply it by diagonal tau here, this one. So that first column will be multiplied by mu 1 over n times u, correct? That first column will be, the entries here will be multiplied by this from the right. And from the left, they will be multiplied by what? So this will be multiplied by mu 2 over n, then the following row mu minus 3 over n, and so forth, correct? So if you take, let's say, this entry here, multiplied from the left by mu to the minus 2 over n, so there it is, mu minus 2 over n, and then you have a mu there, and then you are having this, right? Then you will find that this particular entry is of what order? You will get mu 1 minus 1 over n, right? Which is n minus 1 over n. So you can do the same thing for each one of these, right? Because each one of them will be multiplied by a different power. And then you'll find out that the largest here is that, of that order, okay? Because you see, when you do minus 3 over n, you will get what? You will get minus n minus 2. So it's decreasing, right? Until you get down to 1 over n, okay? And that one, right, that square root of mu is bigger than all the other entries on this column. So this one dominates. And that's all I need to know, that this column is dominated by an entry of this size. Then you can do the rest, right? Okay. The first row is dominated by an entry of that size. The diagonals will have entries of this type, and the off diagonals dominated by entries of that size. That's all, okay? So all I did so far, okay, so this is called, okay, eigenvalue perturbation analysis. You transform your matrix to a form where now it is ready for you to apply the Gershgorin theorem, as you are going to see, okay? So, this matrix is similar to the original B, right? Okay? Now remember the theorem. What does the theorem say? Okay? Assume I have a matrix. I'm calling it A. This A has nothing to do with combination policy, right? It's just a general A. Okay? So take this diagonal element here, A11, and take the sum of the absolute value of the rest on that row. That gives you some number, positive number or zero number, right? Gives you some number, right? So that's the radius associated with that row. Okay? So here, let's say, in the complex plane, I will have a circle centered around this point with radius R1. Okay? Then I'll have another circle centered at the second diagonal with the radius R2. Correct? Another circle at this other diagonal with corresponding radius. You sum all the other entries on that row. Okay, these are called the Gershgorin circles. Okay, so let's say if this is n by n, how many of these circles you are going to have? N. The eigenvalues of your matrix lie within the union of these circles. This is what the theorem says. The eigenvalues lie within the union of these circles. So this is one part of the theorem. Okay. Okay. Now the other part of the theorem, which is also interesting, is if, let's say, if the union of the circles happens to be like this, two disjoint sets, okay? So here it is, okay? So if some of the disks happen to be disjoint, okay? So let's say I have L disks here and the rest here, n minus L, okay? Then L of the eigenvalues will be here, n minus L will be here. The eigenvalues will also split in this similar manner, okay? I'm not proving this theorem, I'm just stating it, Okay, very good. So now, let's apply this theorem to this matrix. Yes?
Is there a mathematical definition of splitting the...
Now, if you can split them, meaning if you can find, as I'm going to do for the current case, if you can find, let's say, a sphere that includes all these circles, right? A sphere in higher dimensions, and another one here, and they do not touch, right? If they do not touch, then they are separable, right? They are disjoint.
So it has to be a sphere that has to separate.
Yeah, they have to be separable.
By
So,
spheres.
well, in hard, if it is a spheres,
I can find multiple, like I can find even three.
I don't know if it is by spheres, to be honest with you, but I think you have to find, let me see, if the set, well, I don't think, if you do something like this, if you just group them together and you get a set in space that's separable from the other set in space, I think that's good enough, okay? And I'm using the sphere as an analogy here, okay? You are going to see, for example, in the problem we are studying, that's what will happen. I will be able to put a sphere around this and a sphere around that, and the spheres will not touch. Okay? Fine? Anyway, you can go and look at the proof for the theorem. I'm not proving it here, right? I will just use this version of the theorem to prove my result, okay? Okay, so where are we now? Yeah, so let's go back to my matrix. So this is my matrix, okay? Where do the eigenvalues of this matrix lie? Okay, the eigenvalues of this, let's take them one by one, okay? What are the diagonal, remember this is I minus lambda, so what are the eigenvalues here? 1 minus lambda 1, 1 minus lambda 2, 1 minus lambda 3, and then lambda, right? So you can see that the eigenvalues of this matrix lie within the union of which circles, right? Or spheres in higher dimension, okay? Within which spheres? They lie within the spheres that are centered at these lambdas, and let's take one of them here. This one, an eigenvalue of b, centered at an eigenvalue of b, and the radius is of this order. Because if you add many of these, n of them times that, it is of this order, correct? And the same thing here. It will be centered at any one of these lambdas, and a matrix of, and a sphere of that, or whose radius is of that order. What did you say? Yeah, in higher dimensions it's a sphere, right? You are centered at one lambda within that radius. It will be a sphere, yes, for each one of them. Okay? Now, okay, so here it is. This is what, okay, let's look at these expressions. So the eigenvalues, these are the eigenvalues of the B, right? This is that 1, 1 block, right? So the eigenvalues of the B that I'm interested in, they lie within a circle centered here, radius of that order, right? Correct? Or the eigenvalues are centered at these lambdas, radius of that order. Fine so far? Very good. Okay? This also means, right, if in particular you take the eigenvalue that corresponds to the largest magnitude eigenvalue, right, so that you get the spectral radius, that the spectral radius of B is this much away from the spectral radius of this B. Okay, and the spectral radius of B is this much away from the largest of these guys, which is the spectral radius of J. So you can get this from that, okay? Okay, very good. Now, remember, I already know that this is less than 1, right? This we know, it's 1 minus O mu, right? What about this? It's less than 1, right? It is strictly less than 1. Let's write it in this form, okay? Let's write it in this form. Okay, now, look here. Okay, so rho of B, I know it is of this form, 1 minus mu, right? That I know, okay? Therefore, these two equations are telling me that the spectral radius is upper bounded by this, or the spectral radius is upper bounded by that, correct? Very good so far. You see, this term here is smaller than this. This term here is smaller than this, and I can choose mu. So I can choose it small enough, right? I can choose it small enough to make this strictly less than 1. And I can choose it small enough to make this strictly less than 1. Therefore, a small enough mu exists that makes the spectral radius of B strictly less than 1. Right? So I conclude that B is indeed stable. Fine? That's the proof. That's the proof of the first part of the theorem. Okay? So I can choose this mu small enough to make it smaller than this, and mu small enough to make it smaller than that, or this plus that smaller than delta. I can do that. Either way, it will ensure that the spectral radius of calligraphic B is less than 1. So proving stability was fine, correct? What is missing? The expression for the spectral radius. Okay? So let me show you a figure first. Okay? Let me show you a figure first. Remember this. So that B is similar to I minus lambda, right? And this lambda is of the order of mu, right? So the eigenvalues of this B are very close to 1. Okay? And what are the distances between the eigenvalues of B? They are of the order of mu. If I take one eigenvalue of B, 1 minus some multiple of mu, another eigenvalue of B, 1 minus some multiple of mu, the difference between them is some multiple of mu. So the eigenvalues of B are multiples, are of the order of mu away from each other. So let's look at the figure, and then this will become clearer here. Let's look at this figure. Okay? Let's look at this figure, okay? So this is 0, this is 1. Okay? 0 and 1. This is 0. This is 1. Okay? Now, remember that the eigenvalues of the matrix B, this matrix B, which is similar to I minus lambda, right? Its eigenvalues are of this, its eigenvalues are of this order, right? Mu max. Okay? So they are around 1, right? Within a circle of radius mu, correct? Okay. And this is real, because D11 is real. Okay, so the eigenvalues of B, actually, they lie on the line, okay, between 1 and 1 minus mu, order of mu, right? So these are the eigenvalues of B. They lie somewhere here. Some of them may be on top of each other, but they lie on that segment between 1 and 1 minus order of mu, correct? And, okay, and the distances between these eigenvalues, right? The distances are of the order of, okay, mu, correct? Are of the order of mu. Fine? Okay. So if you look at one eigenvalue and another, I explained, the order is of the order of mu. So I can find a circle around each one of this radius. This is larger than mu, therefore smaller than mu, right? The power is larger than 1, therefore this is smaller than mu. So I can put a small circle around each one of these to make it disjoint from the other, correct? Okay? If you have a point here and a point there, and this distance is of the order of mu, right? Now, mu to n plus 1 over n is a number larger than 1 here in the exponent. So this is smaller than mu. So I can choose mu small enough such that if I put a circle of that radius there, this will be like that, okay, disjoint. So this part is fine, okay? Okay. Here I have all the eigenvalues of B. They lie in this blue part inside the circle of radius mu, centered at 1, right? And it ends here at 1 minus O mu. Okay. Let's look at the other eigenvalues. The other eigenvalues, they are centered at the lambdas of the J, right? Of the J. These are these x's. Okay? They are all strictly less than 1, correct? Okay, they are all strictly less than 1. Okay, and again, which is just showing what I'm doing here, right? So these eigenvalues of B are in circles around these eigenvalues with that radius, right? With that radius, okay? And for the calligraphic B, they are within these eigenvalues with that radius, which I put around the B's, right? Okay? So here it is. I took, these are the eigenvalues, and around each one of them I put a circle of that radius, because that's what the theorem says. The eigenvalues of the calligraphic B lie in the union of all of these. Now, these x's, they lie within a circle of radius less than 1, strictly less than 1. But this radius is a little bit larger. Why? Because I'm putting a circle around the furthest one of that radius, right? So technically, this circle can go all the way up to here. Correct? So far, right? If you take the furthest away, it will be strictly less than 1, and then I put this much on it, okay? So the radius here is this plus that. Okay, so now, yes?
Mu max to the power 1 over n, isn't that radius larger than mu max?
Yes.
But in the picture, it's...
larger than?
Because it's all mu max 1 over n, right?
Yes.
So let's say n is 5, so it's 1 over 5, which is larger than
over mu.
Yeah.
Okay, and then larger than, which mu you are talking about? Oh, you mean the figure is not in proportion?
Yeah, I mean, won't they overlap?
No. I'm coming there. Of course, the figure is not in proportion, okay? This is of the order of mu, of course, right? They are not in proportion, okay? But now let's talk about the overlap, okay? About the overlap, where is this point? Right? This point is rho of J plus this, correct? If I can ensure that this is less than 1 minus, then they will not overlap, correct? But that's exactly, okay, that's exactly the condition we have here. You see? I said, let's pick mu to make sure. Okay, remember, mu is very, very small. I can always choose a small enough mu, even though this is much bigger than mu, but mu is very, very small, to make sure this is the case, okay? So now you can see, okay, so from here you can get, what is rho? Rho of J epsilon, I want this, plus what? 1 over n, less than this, correct? Okay, so this is by definition 1 minus delta. Plus this O, I want it to be less than this. Which is, you see, if this is satisfied, that condition is satisfied, correct? So these circles will not overlap. Okay, so what you said is correct, but yeah, these figures are not to scale, okay, but you get the point. Okay, so what's the point of saying that they are not overlapping? Okay, all I did so far, I simply told you, explained to you where the eigenvalues are, based on Gershgorin's theorem. But now the second part of the theorem says, I have now two disjoint areas in space, right? How many eigenvalues I have here? The eigenvalues of B, 2m. The rest belong to this set, okay? So I will have 2m eigenvalues of calligraphic B here, and the rest eigenvalues of calligraphic B belong here. Now, which set has the eigenvalue of calligraphic B that is of largest size in magnitude? This set. Because here you start at 0, you are increasing up to 1, right? Okay? And you see, you can see here, you see, this x here, this rightmost x, this one here, is the spectral radius of this B, right? Around it, within that region, you will have the spectral radius of calligraphic B, because this is the largest it can be, right? So you can see that the spectral radius of calligraphic B will be the spectral radius of the original B, this B here, right? Plus of the order of mu m plus 1 over n, correct? Now, what is the spectral radius of this B? You see, it is 1 minus this, okay, the spectral radius. Okay, remember that this comes from D11. Okay, this comes from D11. Okay, fine. So it's 1 minus the eigenvalues of D11. What was D11? D11, if you remember, it was the sum of QK HK, something like that, right? So here it is. Let me. Okay, so I have this. Okay, so rho of B, and then if you remember the expression of, okay, remember D11 is of the order of mu. I can make D11 as small as I want, right? So I can make the eigenvalues of this positive, right? Okay, so then the spectral radius, I can make it equal to 1 minus the smallest eigenvalue, right? Because mu controls the size of that eigenvalue. So here it is, 1 minus the smallest eigenvalue, right? And then if you add this expression to this expression, you get what you wanted. Fine? Took some effort, but that's how you prove that B is stable. In the general case, okay? In the general case. Okay? So let's continue. So that was part of what I wanted to prove. You remember the second part? Okay? There was a second part, but I'm going to come there. Okay? Before I get there, I want to show two intermediate results which we are going to use next time. But this is the time to show them. Okay? They are not related to the strat. So I'm taking a digression now. Okay? So by the time I come back to the second point, you would have forgotten it for good. But okay? I'm taking a small digression here. Okay? I'll show you quickly the algebra. I don't need to go through all the details, but remember, okay, this is my matrix which is similar to B, correct? Okay? You are going to see, especially next time when we do performance analysis, I want to know how well these algorithms perform, that inverses of this transformed B of this form will come up often. I minus B inverse or I minus B bar inverse. This will come up, okay? But because I know each one of these is of the order of mu, I can also take this matrix, partition it, and tell you what's the size of its partitionings. That's what this theorem is saying. Okay? That's what this theorem is saying. Fine? Okay? So I will use 229 a lot next time. So that's why I'm mentioning it here, because it relates to the partitioning of B. So let's prove it, okay? This is just simple algebra, okay? So I will not go through all the details. I'll just give you the idea. So I already know what B bar is, right? This is B bar, correct? I minus B bar, you subtract I minus, right? I minus, right? So this I cancels out. This becomes plus, plus, you get I minus here, right? So here it is. This is I minus. Fine? I want to invert it and find the size of the entries. How do you invert a block matrix? This is a block matrix. Well, there is a block inversion formula, right? Okay? You saw it in 210A. Okay? And before I invert it, for example, D11 is of the order of mu. Obviously, this is of the order of mu. This is also of the order of mu, right? This is of the order of mu, and this is of the order of 1. So we know the sizes of x, but now let's invert x, right? So when you invert it, I'm going to use this block inversion formula. Okay, this is the block inversion formula, right? So the inverse of the block in terms of the inverse of the 1, 1 entry, okay? If you don't believe me, then just multiply the right-hand side by A, B, C, D, you get, what should you get? Identity, block identity, okay? Which is the identity, right? So, fine? Okay, this delta is the Schur complement, okay, D minus CA inverse B. Of course, this particular expression assumes A is invertible. Okay, if A is not invertible, you can do it. Okay, for example, you can also have a similar formula using the inverse of D instead. So if you apply this to x11, x12, x21, x22, here you get this. Fine? Now let's look at this. Okay, what is the order of delta? Okay, this is mu. I'll do it quickly because this is simple, okay? This is mu. 1 over mu, mu. So this is mu. D was 1. So delta is of the order of 1. Fine? Okay. So let's come here. This is 1 over mu. 1 over mu times mu cancel each other. 1 over mu times mu cancel each other. This is 1. So you will get what? 1 over mu. 1 over mu dominates 1 when mu is small, right? So that's how we get 1 over mu here. What about here? Mu, mu inverse 1. You get 1. You get 1. You get 1. That's exactly fine. So that's why I wanted to show this result now. Okay, simple, okay? Not really, I don't need it, but I'm showing it now because I will need it in the next lecture. And there is another similar result I will need, okay, which I'm also going to prove, and then I'll go back to what we were doing, okay? For that, remember the definition, you know what the Kronecker product is, and then I defined earlier the block Kronecker product, okay? So A and B are matrices with block entries, A11, A12, A13, these are block matrices, right? Similarly for B. So I can define the block Kronecker product. How do you define the block Kronecker product? I defined it to you before. Here it is. The block Kronecker product will have blocks. Each one of these blocks is defined in terms of the original Kronecker product. You take, let's say, block 1, 1, 1, 1. What do? You take A11, you Kronecker product it with all the blocks of B. A11 with B11, A11 with B12, A11, right? Take this A11 Kronecker product with everybody. That gives you K11. And you move to K12. You take A12 Kronecker product with everybody. Right? That's how you... It is Kronecker products like this that come up when we study evolution of networks. Okay, that's why you already know why. Because when you define these block vectors, they are block vectors, right? Have subvectors in them. The matrices have submatrices in them. So that's why these quantities come up. And the block Kronecker product has useful properties similar to the standard Kronecker product. I will be using now 2 and 3. Okay. Here it is. If you have the Kronecker product of two products like this, you can distribute it like that. Traditional Kronecker product, block Kronecker product. Okay, you can write everything in terms of the original, of the traditional Kronecker product if you reverse the order, if you change the order of B and C. Fine, these are properties, you can prove them, okay? I'm going to use them. So what is the next result I want to show? This is the next result I want to show, okay? Again, it's not related to what I need, but I will use it next time. This matrix will come often in our analysis. This is the B. B will come often. We showed today that it is stable and we found its spectral radius. But this matrix will also come up. B Kronecker product, block Kronecker product with its transpose. B transpose with B star. This matrix will come up a lot. You'll see next time, okay? Again, I want to know what is the dimensions, what's the order of its entries. Just like I showed for I minus B bar inverse, I would like to do the same thing here. Okay? How I'm going to do this? Well, each B, this B, I know how to write it as a V submatrix involving D's, the V inverse, right? So I can put the transpose of that here, the star of that here, right? And those D's, I know their orders, right? Mu, 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 right? So if I use that information, then I'll get the result, okay? That's the idea, okay? So, again, similar result for I minus F inverse, right? That's what so actually I'm showing two things in this lemma. One is, okay, so what is the F bar related to F? Just like the B bar is related. The F bar is when you take the F and you multiply it from left and right by the eigenvectors, just like we did with B to go from B to B bar, okay? To go from B to B bar, we multiplied by V inverse. To go from F to F bar, we multiply by the Kronecker product, okay? But because it's a bigger matrix here, okay? So this lemma is showing two things, okay? It's showing two things. That the entries of I minus F bar inverse again are of this type, just like I showed, okay? Similar argument. But more importantly, and this will be crucial, this is a big matrix, right? Big matrix, right? Block Kronecker product of matrices that already have Kronecker products in them, right? It's a big matrix, okay? If you try to run simulations coding it in MATLAB, you will run out of memory. You need to know how to do it, okay? If you just do it the usual way, you will run out of memory, okay? Well, with today's computers, right? You never know. Maybe tomorrow you can run it. Or you understand why? Because this F is very big, okay? But anyway, there are ways around it. Now, but here I have a rank 1 approximation for that inverse. Okay, I'm going to show that this inverse matrix here can be written like this. This is the Perron vector of P, Kronecker P. So this becomes a tall vector. 1 Kronecker 1. This is another vector, right? So this is like a column times a row, right? Kronecker, a matrix Z, shown on the next slide, plus a term of the order of 1. Okay? This term will dominate because it will have 1 over mu in it. Will dominate this. So this is small actually compared to that. What is this Z? This is the Z. Okay? So what is the Z? You are adding multiples of the H's. However, they are enlarged because remember the F was B enlarged, right? Kronecker product B with itself. So you enlarge the H's here, H and H transpose. Because in the complex case, H transpose is not H. It's not symmetric. It's Hermitian, right? So this is Z. Okay? Remember, Z has Q, which has mu. So Z inverse will have 1 over mu. Right? That's what I said. Okay? So this second lemma is showing this. Okay? Okay? So I'm going to go through this argument quickly because it's just algebra like the previous one. Okay? I already showed you what B is from before. This is B transpose. This is B star. Okay? Introduce the eigendecomposition for P. Okay? Then you will be able to write B star in this form, just like we did for B, right? These are the eigenvectors, and in the middle call them E's, because this is for B star, not for B. For B, I call them D's. For B star, I'm calling them E's, okay? You do the same thing. The important thing, they are still similar to D's, right? So I'm not going to go through that again. For B transpose, again, the same thing, I call them D's because they come from the same B, right? They are of the order of mu again. Okay? So now you do the Kronecker product of this B with that B, right? Okay, so when you do that algebra, you will find that your F is given by this expression where X is this block Kronecker product, okay? Now, I'm interested in F bar. So take this inverse there, take this there. That's essentially the, right, F bar, X. I minus F bar. So I'm interested in I minus X, showing I minus X inverse, right? Okay. Well, I already know what the entries of X are. Take this Kronecker product, this, and take this Kronecker product, this, right? Okay, so this is just algebra, tedious algebra, but you can do it. Okay. So this is the X. Okay, here it is, right? The 1,1 entry of X is this Kronecker product, this. This is just to show you that the entries of X have these dimensions because you can express them in terms of the E's and the D's. Okay, there it is. Now invert this, apply the matrix inversion lemma, and use the fact that each one of these X's are like this, you will get the result that you want. Okay, I'm not going to go through that. You get the idea. Very similar to what we did before. Okay, so I'm going to skip that. Okay. Now, what about the approximation? Well, when you apply the matrix inversion lemma, sorry, not the matrix inversion formula, right? The block matrix inversion formula to this inverse, This is a 2 by 2 block matrix. You'll get something plus a correction term. That term is of the order of 1. That additional term will be of the order of 1. Okay? X11, I know what it is, but that's exactly the Z inverse. Okay? So if you just do the algebra, okay, you will find that I minus X inverse, okay, which is related to I minus F bar inverse, is the expression I showed you before. Okay? Here it is, okay? I'm not going to go through this algebra, but the idea is I want to show that I minus F inverse can be written like this rank 1 expression here plus of the order of 1. Okay? Well, I just showed on the previous slide how it relates to I minus X inverse. I gave you an expression for I minus X inverse in terms of Z. Just plug it here and go through this algebra. Okay, this is simple algebra using the two properties of Kronecker products I showed you before. Okay, I'm not going to go through this. You see, if you don't believe me, so let me just do one of them quickly. You know, the first line comes from the previous slide. Okay, so Z inverse, I'm writing it as 1 Kronecker Z inverse. Okay, so you see here, these two Kroneckers, I can group them together. P Kronecker P, so this I Kronecker I is that I. And then these two, I can group them together. P Kronecker P times 1, I times Z inverse. Okay. 1 Kronecker I, this is this I. Okay. And then again, you can group them together. You see here, 1 Kronecker 1 with P Kronecker P, you get that. I Kronecker Z, you get that. So you get what I showed you before, okay? Anyway, these lemmas are not difficult. You just have to follow the arguments, okay? They are not difficult, just linear algebraic derivations. But you need to know they exist, and next time I'm going to show you why they are useful, okay? Fine? Okay, so what I want you to remember is that both for I minus F bar and I minus B bar, I showed that their entries are like this. And I gave you an expression for I minus F inverse. Okay, I'm going to use this expression next time. Okay? And the derivation is just algebraic. You can follow it. Okay? Very good. So now, let's come back to the question we started with, right? Which is to show, right, that the norm of the mean error, right, enters an area of size mu as I goes to infinity, correct? Okay. To do that, like I did in the single agent case, I need to introduce a smoothness condition on the Hessian matrix, okay? We need to assume that the Hessian matrix is smooth enough around the Pareto solution. And by the way, again, I showed you that logistic regression satisfies this, mean square error cost satisfies this, right? For some useful costs, we know that this is always satisfied, okay? So if you perturb a little bit away from the Pareto solution, the Hessian matrix, for example, in the mean square error case, this is a constant minus a constant. So 0 is always upper bound, okay? And in the logistic case, you also have a bound. So under this condition, okay, we can show that this is of the order of mu, okay? So how do we show that? Okay, how do we show that? So let me show you how we show that. Remember, what was the recursion? Let me write it here. Constant what was the other term? I think here I had A transpose MC, and this term here, what was that? I think, was it A2 transpose MB, something like that, right? Was it a minus? It was something like this, correct? We showed so far that B is stable. So that we have, okay? Now you see, if we did not have the last term, if we did not have the last term, that's just a deterministic recursion, right? Driven by a stable B, W tilde would converge, right, to some limit, because A2MBE, that's a constant driving term. But I have like a random process feeding the system, okay? Now, proving what I want to prove is very similar to what we did last time in the last lecture. So that's why I'm not going to go through all of the argument. I'm just going to put it in a form similar to what we did last time. And then I tell you from this point onwards, you continue like last time. You see, what do we do now? Remember that this B, right, this B is similar, right, to something like this, a B bar, right? Correct? Similar to a B bar. This is the B bar. So just take that recursion multiplied by V inverse. I don't remember if it was V inverse or V inverse B, but you get the point, right? It is similar to B bar. So just apply a transformation here, right? Let's say multiply by V inverse here, right? Multiply by V here, V inverse, and then V, right? So this becomes B bar, correct? This becomes a transformed vector. I call the top part W bar, the bottom part W check. Okay? If you do the same thing here, okay? Remember that I argued last time, because of the definition of the Pareto solution, that second term will have this form. Its B bar will be 0 and B check will remain. You remember this? Okay? And then the last part, here it is, I multiply by V, so it's V transpose, so I have it there, okay, so it's V transpose here, calligraphic, okay, calligraphic, V minus T, because, okay, fine. This is just a change of variables, correct? I did this last time, a change of variables, so that you get this B bar here, but this B bar we already know is stable, okay? So let's examine this term here, okay, let's examine this term. Remember, I had C. What was the definition of C? I think it was the expected value of the boldface H, something like this, I believe. Something like that, okay? So because I have a bound on the norm of this, I can bound this. So let's look at that, okay? So first of all, remember, the definition of H tilde, this is at each node, is the difference between the constant H and the random H. Now I can use here, right? Remember, the constant H, this is the constant H. The random H, this is the random H, right? That norm is less than or equal to the norm of the integral. That norm is equal to the norm of the integral, which is less than or equal to the integral of the norm. Right? There are two steps there, correct? Okay? Because this is equal to the norm of the integral, right? The integral of this constant is itself. Okay. But from the assumed smoothness condition, right, this is bounded by the difference, correct? Here it is, bounded by the difference. Okay? Okay, very good. But phi tilde is related to W tilde, right? Remember that. Phi tilde, right, is a combination of the W tilde. Apply Jensen's inequality here because this is a convex combination. You can move the norm inside. Bound each A by 1. So I'm going quickly here because you have already seen these arguments, right? So this here, I'm adding the W tilde over the neighborhood. I can add the extended version over the neighborhood. Obviously, this is upper bounded by this, because, right? I can add the W tildes over the entire network, right? You will get something like this, okay? So now, right, because each one of these is less than that, so I have n times, right? But the important thing, what's the important thing? The important thing is that this H tilde is bounded by the norm of W tilde. Okay, good. So now let's go back to C. Okay, so if each one of these is bounded by the norm of W tilde, the norm of the block diagonal is obviously bounded by the norm of W tilde as well. Fine? Okay, so now let's go back to C. You see, this is the norm of that last term driving your dynamics, right? So this is upper bounded by the norm of this, the norm of this, the norm of this. Now the norm of C. This is the norm of C, correct? Very good. Okay. Well, the norm of an expected value, again, from Jensen's inequality. So here you can put a switch, expected value of the norm, correct? Okay. This A came out. So now here, you see this norm is bounded by W tilde, and then you have a W tilde here. So you will have expected value of W tilde squared, correct? And this we already know is of the order of mu, correct? In the limit, right? And then you have another mu here, right? So all I need from here is that driving term that I'm going to argue that it is a small, you can see it from that driving term, okay, in the limit as I goes to, because I know that the network is stable in the mean square error sense already. I know that in the limit, this is approaching mu. So actually, this driving term is of the order of mu squared in the limit, okay? This is the first conclusion. What did you say here? This is the definition. C has the expectation in it. C, no. C, if you remember, right? I told you would forget, right? C had an expectation in it, right? If you go back to slide 3 or 4, okay, there is an expectation in it. Remember, how did we get C? We took the random H, we split it into a constant, the random B, we split it, right, into a constant B. The random B was multiplying W tilde, right, under expectation. So that term goes into C, right? Okay. So because of that, okay, so here it is, okay, mu squared, okay. Very good. So if I go back to my recursion, so this is of the order of mu squared, mu maxi squared, right? Okay. So just to simplify notation, I can call this Z, let's say Z bar, Z check, okay? Call this C bar, C check, just to keep things simple, because now it becomes everything deterministic in this recursion, okay? Here it is. Okay? This comes from B. B is on mu, correct? Now, this recursion has the same form as the recursion I studied last time. Okay, very similar, okay? Very similar. Okay, I had a recursion when I was studying whether the error vector is stable in the mean square error sense. I had a recursion like this, where here I had the expected value of W bar squared, here I had the expected value of W check squared, the same thing here. I had a matrix here where all the entries were mu, 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 mu with a J, and I had a driving term BE here, or mu, and this is a new driving term here, mu squared. Okay, so the only thing is that before they were random, now they are constants, but they are of the same order of magnitude, okay? Here it is. These we already know that, correct? Okay, so if you follow exactly the same argument I did last time, I will show you one slide just so that you see that indeed it is exactly the same argument, okay? You will be able to show what was the argument. Let me just remind you, maybe in words, here. Z bar is this times Z bar plus this times Z check plus this plus 0, correct? The norm of Z bar squared will be upper bounded. You apply Jensen's inequality, right? You have here the sum of two terms. You multiply one by T over T, the other by 1 minus T over 1 minus T. Apply Jensen's inequality to separate them. You do the same thing for the second, okay? I have these slides if you want to show you. If you follow exactly the same arguments, that's how you arrive at a recursion like this, okay? Where I told you exactly what the entries of this gamma are, but more importantly, what the entries of I minus gamma inverse are, okay? Where this is a driving term here, and these driving terms will be of this order, okay? Once you get to this point, you can conclude now right away what's the size of this, what's the size of that, right? I minus gamma inverse times this plus that, correct? So this is now simple. You understand what I'm talking about here? Okay. So if you do that, you will be able to conclude that z bar goes to mu squared, z check goes to mu squared, okay? Z, which contains z bar, z check, goes to mu squared. Therefore, the norm of z goes to mu. And the norm of z by definition was w bar, w check under expectation. That goes to mu. And now I know how these quantities are related to the original w tilde, right? Because the original w tilde is a transformed version of this. Therefore, up to a constant, it is exactly the bound of that, correct? And you get what you wanted. You see? So to get to this result, what you need to do is to, recursions like this will come often in our analysis. That's why you need to get used to it, okay? You will get recursions, and then you apply Jensen's inequality to transform them into inequality recursions like this, where you know the sizes of the quantities, and then you take the limit, you conclude the size of the limit value. You understand? Okay? So just so that you believe me, okay, let me show you quickly. This is the recursion, right? This is the recursion that tells you how the mean evolves, okay? How the mean evolves. Okay? We already did that here. So take the first recursion, right? The first recursion was this times z bar, this times z check, and c bar, right? And then just apply Jensen's inequality. Remember how we did it? You multiply by 1 minus t, t over t, right? The norm of this we know that. Then you pick t to cancel one of this. Okay? Then you get a recursion like this. And in the limit we know that this is mu squared. Then you repeat for z check and you put them together. Okay? You repeat for z check. Okay? t1 over t, 1 minus t, 1 over minus t. And then you put them together. Now you pick the t to be rho plus epsilon so that you cancel that. Remember we did this, it's exactly the same argument, okay? When you put them together, this is the A, B, C, D, E, F, and you arrive at that recursion, okay? So this is what I just showed you. Mm-hmm.
So this is the norm of the expected value.
Yes.
And this is a lower bound of the expected value of the norm, right?
Yeah, what I know, this quantity here, we know it goes to something like this. This is what we can conclude from what we proved last time.
But why do you think this is a lower bound? Because this is on the norm of
the size of the expectation. This is the size, this is essentially a bias, right? This is how far you are from your ultimate goal, right? So this is measuring this is on average how far you are from it. This is measuring the norm of it, the norm of that error. So I'm telling you that error is still of the size of mu. Okay? Over there, I'm telling you that on average, the norm of that error is mu to the 1/2.
This is an upper bound to that one, right?
Sorry?
This is an upper bound to that one.
Yeah.
So what we can tell also from this that this is a lower bound of that, of the expected value of the norm. We can say it's of that order, it's a lower bound.
This one here?
Yes. This is a lower bound of the expected value of the norm, right? Using Jensen's inequality, the norm of the expected value is lower bounded.
Right, yes.
So the expected value of the norm is lower bounded by all mu.
Right. Yes.
So it's not the same as saying it's of the same order, right?
Oh, no. I'm saying this is of this order, right?
Yeah.
Right.
But why this is important for us? It's the norm of this.
No, because it's a useful result, right? Because what this is telling you, this is the error, right?
Yes.
This is how much error you have on average, right? This is the size of your error. You see, right? This is the size of your error on average, which is essentially a measure of how much bias you have. So I would like to know the size of that, right? So this is telling me that size is of the order of mu, which is a better conclusion than saying something like that, right? Than saying something like that. You understand? Okay.
But so for the first order derivative,
Yeah.
which is more common in the literature? It's called the convergence. Is it the expected value of the norm or the norm of the expected value?
No, which is common in the literature is studying this quantity, right? The mean error evolution, right? If you can show that this goes to 0, then we say that the algorithm is asymptotically unbiased, right? So this quantity is useful, okay? Here, what I'm showing is that the norm of this quantity is small, okay? Is small, okay? Now, for that quantity, we derived bounds for the mean square error and the fourth order moment. So these other quantities are very useful because they are variance type quantities, right? This one is showing that the mean has a small norm, and the other is showing that the variance has a small norm, okay? So if you put them together, then you get something meaningful, okay? You understand? Okay? So this is what I wanted to discuss with you today, but the main thing that I would like you to remember is that it takes some effort, right, to establish that these networks are indeed stable. So it's like I always tell you, deriving an algorithm is not that difficult, but showing that it will perform and it will be stable, it takes some effort, as you can see from these two lectures. Today, I introduced this constant dynamics matrix B, calligraphic B, which is defined in terms of the constant Hessian matrix H, in comparison to the random B. Remember, you had a random B, and then I transformed it into a calligraphic B. So that B will be very important for us. Today I showed, using Gershgoring's theorem, that it is stable, and I gave you an expression for the spectral radius of that B. These results will be useful in the next lecture when I study the performance of the network, right? So this was one conclusion that I had today. The other conclusion was that I showed you the size of the entries of I minus B bar inverse, I minus F bar inverse. These are matrices that are similar to I minus B and I minus F, right? I showed you that their entries are of similar size, 1 over mu, or order 1, order 1, order 1. And I also gave you what I refer to as a rank 1 approximation, right? A rank 1 approximation, or a low rank approximation to I minus F inverse, which will be used next time. Fine? So, good? Okay, so I'm going to stop here today then.